Welcome to the dynamic learning hub of ExcelR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a live classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Want to get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. ExcelR. We don't just train, we build careers.
Yes, so the collaboration with ExcelR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course, and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching, and it was fabulous.
This was a great experience for me. So I would absolutely love it if ExcelR and its team would come again to our campus and conduct more events like this.
It was a great course, and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with ExcelR was very smooth. They helped us in conducting the workshop smoothly, right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank ExcelR for being a part of it.
I was very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later for my college, I get to know about ExcelR and I enrolled in ExcelR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good teacher. He not only focusing on theory part, he is doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they are also conducting different exam to test our knowledge, and as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, ExcelR.
Recently, I was searching for digital marketing courses online in Google, and I came across ExcelR, and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped. So I came to the ExcelR office in Bengaluru. This digital marketing course has helped my career and my skills to develop, and the certificate has helped my company to join. Thank you, ExcelR.
I came to know about this course from my college. Actually, for learning platform, this is very nice, and I learned from here ChatGPT and AI from online. Because he's teaching for me for AI generative and ChatGPT. We are using this technology in more. And after finishing the courses, I came from for collecting the certificate. I seen the classrooms and faculties. Classroom is very nice. After the completion of exam, they will give gift and certificates. Thank you, ExcelR, for giving these courses. I learned a lot from this. I gained the more knowledge from here, and thank you for ExcelR for teaching us.
Hello guys, I'm Vikram Mahajan and I'm studying in Swami Vivekananda Institute of Technology College, and I came across a training program which was mobile app development using Flutter, which was given to us by ExcelR Solutions. I came across this program through my college faculty, who told us about this program, that it is a very good course and you should enroll in this course. So I enrolled in this course, and initially I felt really good about this course because they started everything from a very basic point of view, that even if someone who doesn't know
Good afternoon, dear faculty members. I hope you all doing well. I request please inform your colleagues to join the session as we will start for the day now. I request if your colleagues are not joined it, please ask them to join it immediately. Okay, we will start for the day, and it's a good afternoon.
Good afternoon.
Yeah, you can start the session.
Yeah. Okay. Good evening, all. I'll share my screen. I hope it's visible.
Yes, sir, it is visible.
Okay, thank you. So today is day 4 of our quantum computing course, and yesterday we discussed quantum computing advantage, and the day before that we discussed about quantum computing basics. In quantum computing basics, we learned about qubits and one of the implementation of qubit, that is electron spin. And after that, we learned how to represent the qubits in an abstract space, in a vector space, for instance, and also in other spaces like in a block sphere, and also as a matrix. We also learned about how to perform various gate operations on the qubit, which are fundamentally different from the classical gates such as AND or XOR. Rather, we used gates such as Hadamard, X gate, Y gate, Z gate, etc. We also came across a new type of gate, query gate, which performs query model computation. And in the last class, we particularly focused on the advantage of quantum computing over the classical computing. What is this hype about quantum computing? It has certain advantage, also called as quantum supremacy. And we demonstrated that in a very simple example, which turned out to be the very first quantum algorithm. That is a Deutsch algorithm. And in the Deutsch algorithm, the query model has a function f whose structure is unknown to us, but it's only thing we can understand about the function is whether it is a constant function or a balanced function, and by how many number of queries we can estimate the nature of the function is the question asked. And through the processes of classical computation, we need to make two queries to understand whether a function is a constant or balanced function. And that function is a Boolean function and a single bit function. Through the means of quantum algorithm, specifically the Deutsch algorithm, we understood that it's constant or a balanced function with only a single query. And thus the very first quantum advantage is established. There are other algorithms as well, which also have advantage over the classical computations, like the Shor's algorithm, which have a polynomial advantage over the integer factorization problem. In the classical case, integer factorization problem has an exponential complexity. Apart from that, we also apart from that, there are other algorithms like Simon's algorithm, which also has a significant advantage over the classical algorithms of some specific problem. And Grover's algorithm, which is used to find out a particular search key, a specific search term in an unsorted list, and it was able to do that, find out a search term with an order of square root of n, where n is the number of elements in the list. that demonstrates a quadratic advantage over the classical search algorithms. So with that foundation, we have sufficiently learned things in the abstraction space. So today we are going to come out of the abstraction space and delve more into something which is more practical, and that is the implementation of qubits in physical devices and physical architectures. So before that, I will quickly go through the building blocks of a quantum computation architecture or a quantum computer. So a quantum computation, it is not a replacement to a classical computation. So as we have seen, if you have, we have discussed about adders, like half adders and full adders in the last class, right? To particularly to understand the complexities associated with those circuits. And now a quantum computer is not a augmentation to your classical computers. Rather, your classical, it's not an extension to your classical systems. Rather, the very basic foundation of quantum computation lies in the principles of superposition and entanglement, which have no classical analog. Since our brain is wired to understand the everyday objects and the behavior and kinematics of these objects, it is very unnatural and non-common sense to analyze and perceive the quantum way of things. We also demonstrated this using a Qiskit software demonstration yesterday, coding demonstration, where we took an informal kind of example, that of a coin being tossed, and how it can be analyzed from a classical point of view and a quantum point of view. So we were able to appreciate the principle of superposition in such a simple experiment as coin tossing. Then what is a quantum computer if it is a completely new concept? And how is it going to help us in our practical everyday activities? We are very much familiar with the evolution of the gadgets, specifically the electronic gadgets, which were many decades ago. We had a calculator which has computed different functions and calculations with a specific speed. But today we can perform that using specialized software tools with much greater speed and accuracy and precision. A quantum computer is not made or not envisioned to help you with a faster computation of your common calculations like addition, multiplication, or something like that. But rather, it's specifically for helping you to compute very complex problems that scale very fast with the number of inputs or the number of units, number of inputs. So if I have integer factorization, for example, it scales up very quickly with the number of inputs, and hence we need a quantum computer to calculate it. And this is something similar to having a graphic card in your computer or an FPGA augmentation. These are specifically directed for doing some specific tasks and not for helping you do your everyday tasks faster. So a quantum computer can be connected to your classical computer in the form of an accelerator, quantum accelerator, and help you with specific tasks. For example, if you are a chemist and you are working with modeling of a particular chemical molecule to probably manufacture a new kind of drug that specializes uh, in treating a very new disease, then you will consider your quantum accelerator to help you with um, efficiently and quickly model your molecule. So that is a main function of a quantum accelerator. And in this connection, people often have confusion regarding what a quantum computation really is. And one of the main confusion is that of quantum parallelism. Yes, it's true that quantum parallelism is a valid concept, but the way we understand about it has a problem. So the last 3 days, I've been talking to you about the two main principles, the superposition and entanglement of quantum um, computation. So these are two topics which recur all throughout the study of quantum computation or quantum computing. So if you see the principles of how the superposition work, you can understand that it's sort of a parallelization, right? You have a particular state vector get psi, and that is representing a physical system in the real world. Let's say it represents an electron, or rather an electron spin. And now it exists in both the upspin as well as the downspin. So how can an object exist in both? And that is the superposition principle. And when you use these kinds of fundamental units called qubits in the computation, people might think that it takes multiple paths to the solution. If you have a set of problems and you find answers to all of those problems parallelly, and that is what is called quantum parallelism, which is a wrong understanding. It's a totally wrong understanding. Rather, the quantum parallelism simply means that it just explores, or it exists in the multiple states or multiple solution paths. And the very act of measuring the physical state makes it collapse into one of the states. And there, your parallelism is completely, uh, it is gone. You will be given only a particular classical value, and that's it. That's it. So finally you will get the answer, the one and only solution to that problem, rather than solving multiple problems parallelly. That's not the understanding of quantum parallelism. So algorithms like the Simon's algorithm or Shor's algorithm, they utilize this quantum parallelism concept, where I have seen in the Deutsch algorithms case in the last class, where the system evolves into multiple states, 0 and 1 states, and having the 0 and 1 state allowed allowed the input state to evolve into a state where we can just by measuring we can understand whether the function is in an odd state or an even state, right? So if you work out that, you will able to understand, appreciate the principle of quantum parallelism. And along with quantum interference, That comes into picture when we apply the operators. It allows us to understand about the problem or the solution or what the problem is asking for. In the Deutsch case, the solution was asking for whether the function is constant or balanced. We will be coming to the point of solution as we pass each gates. So here in the building block, the algorithm of the problem, the quantum algorithm, that is the highest level, such as the Deutsch algorithm, the Simon's algorithm, Grover's algorithm. These are methods by which we can find solution to complex problems, which are very hard or perhaps impossible for classical computers to solve. Having these algorithms, they are mapped onto a language, such as in the last session we did the software Qiskit session, in which we used the Python language to map the to draw circuits and to make quantum bits, the quantum gates, and doing do calculations using that, and also readout, which is just nothing but the measurement. We did a histogram plot to understand the result of our multiple trials of the experiment, of the rather the code execution. And this language is a higher language, or a high level language, and this needs every programming language needs a compiler to compile the different lines of the code and convert it into an machine language, which is a lower level language which the machine understands. And after that, it needs to be passed on to various units, such as the control unit, the ALU, or arithmetic logic unit, which in the case of quantum are fundamentally different from that of classical computer. In the classical computer, you send signals in the bus or the interconnects, and these go to different units, such as the ALU, which takes in the input and does processing like addition and subtraction or multiplication, and then it gives out the output again to the bus, back to the central processing unit, and also the memory, it retrieves the data from the memory and things like that. But here in the case of quantum, this is not how it works. It's fundamentally different. And this kind of compilation, right? This kind of units, they all subscribe to an instruction set, a quantum instruction set, which is able to connect these units together into a physical microarchitecture, into a layer called microarchitecture. And the microarchitecture contains various physical units, such as the interconnects, your qubits, which are physical qubits, are lying on the chip, and these are also connected with various lines for probing and reading out, and various other lines, depending on the different platforms of qubit implementation. So that is the final level. The lowest level is a chip where all these things are situated. And we also have additional layer called error correction, depending on the platform. Again, for platforms like the topological qubits, they don't require an error correction separately, which is laid in the hardware setup itself. But for most of the platforms of qubit, implementations, we need an error correction so that the error that comes into the that interferes with the qubit, the state of the qubit, can be removed or can be corrected, and thus a more robust answer and a robust functioning it can be ensured. So finally, the way the quantum computers work is we perform multiple runs of the same experiment or the same problem, and the answers that you get, we average them out, and the particular state which we get as the answer, if it has got the highest frequency of occurrence, or if it has the highest probability, or if it has the highest the tallest histogram bar, then that would be the answer to our question. So this is how it was. So in order to understand the qubit implementation, the most important factor here, or the current research focus is on the quantum materials, because quantum materials forms the environment where the qubits live. And the environment is very important for the qubits because qubits, a single qubit has two primary functions, and that is to first one is to associate with its neighboring qubit so that functions like 2-qubit gates can be performed. And second one is to interact very less with the environment, except for the case where a readout happens. And this is because the environment can act as an external observer that accesses the information in the qubit, and thus it destroys the state of the qubit altogether. And this is not observed in the classical system, where even if a classical bit is observed by thousands of external agents, the information stored will remain secure. So that's a huge challenge in the case of storing qubits. And in the timeline of the evolution of quantum mechanics development, there are two major phases. The first one is termed as the first quantum revolution, in which great stalwarts like Einstein and Niels Bohr laid the foundation, and we were able to understand, explore the microscopic nature of the matter. And the result of that is actually sitting in our hands in the form of mobile phones and laptops and computers, which contains the chips where the millions of transistors are integrated into it. This is the result of first quantum revolution, which took over 50 odd years to create the first transistor, and further more years to miniaturize them and come to the point as it is now. Whereas today we are going through a second quantum revolution, which deals with a different aspect altogether, where we are trying to successfully design a quantum computer, which is like the pinnacle of this revolution, which is like going to the moon kind of a situation for this second phase. And this is the second quantum revolution. And here the qubits are the fundamental unit, and thus to implement them has a very important role. And to implement qubits, we need to know about the quantum materials, how they are synthesized, how they are characterized, and how do we manipulate them so that the desired properties are induced in them, and thus we can learn more and also design better qubit systems, or the quantum computing chips. So as a prelude to that, a very important technique which people or the people involved in the community of material science use is called something called thin film synthesis, and in that something called a pulse laser deposition, which is one of the many techniques people use to grow a thin film. Now, what is a thin film? From the electronics point of view, we know that every single integrated chips, they are designed on a silicon wafer, right? And on top of the silicon wafer, people deposit thin films such as chromium, and on top of that, something like a gold, which acts as a metal, and chromium is an adhesion. So these are in the very small, minute scale, such as a nanometer scale, or in some cases micrometer scales, and thus they are called thin films. And this synthesis of these films are not very trivial, because there are so many factors that needs to be adjusted to grow thin films, such as the maintaining of the crystalline properties of the material. So every objects or every metals like silicon or germanium, they have a particular lattice structure in which the atoms of silicon and germanium, they occupy uh, certain locations in space in an ordered fashion called as lattice. And now, to grow a thin film means we are going to a very nanometer scale, length scale, and putting these atoms on top of another material, which is called as a substrate. And these atoms will have an attraction or a low energy sites on the substrate where it occupies, and that results in a shift in its lattice structure altogether. So if the lattice structure was something else before, when it comes and sits on the substrate, its lattice structure will change. And the result of the change in lattice structure will be reflected in its electronic properties, such as, let's say, the band gap of the material may change. And if the band gap changes, remember yesterday we talked about the two-level systems of the qubit. Now, the two-level system means there are two energy levels, and in between the two energy levels, there is a gap, and that is the energy gap. So tuning of the energy gap is crucial to manipulate and drive qubits. So in order to grow films or grow thin films having the required property, we need to have a robust, a very good technique. And so here is a technique called pulsed laser deposition, or PLD in short. So where we use a PLD chamber, which is a vacuum chamber, in which we connect two important objects. One is a target object, another one is a substrate. So I already talked about what is a substrate, that is upon which the thin film is grown. And now a target is something which is like a precursor material, which means if I want to grow silicon, then I use a silicon here, right? But it's not a thin film, it's a bulk. So now I want to bring silicon on top of the substrate. So I need to excite the silicon atoms and ions which are on the target using some method, and then I control the atmosphere within the chamber such that I get the desired way of growth on top of the substrate. And for that, I fire a pulsed laser beam, which has a very high energy, onto the target. and it heats up the surface layer of the target material, where the atoms of silicon gets agitated by the intense laser beam, and it ionizes, which results in an expulsion of ionic uh, um, ionic matter, which gives out light due to the excitations, and along with other counterparts like the electrons and neutral chemical species, and these are directed towards the substrate, and under suitable temperature and suitable oxygen pressure within the chamber, I get a thin film of desired properties on my substrate. Now, after the formation of the thin film, I need to check for the correct properties. So the first thing I do is, so I do a series of things to check for that, and these are called characterizations. And the first characterization I do is the XRD characterization, or X-ray diffraction characterization, in which I pass X-ray onto the film, and then I detect the scattered X-ray coming from the film. And now the thing about X-ray is that the wavelength of X-ray is about 1.5 angstrom, and these are the lattice parameters, and hence the X-ray having the same wavelength can easily probe or easily identify the lattice spacings in the crystal, and hence I get what kind of a crystal structure has been formed on my substrate. I get an understanding of that from X-ray or XRD characterization. More than that, XRD can also help us understand about other things like the composition, the strain in the film, the morphology, and various other properties of the film. So that's the first characterization. Secondly, I can also measure the band gap of the material that is grown as a film on top of the substrate. So one of the techniques to measure the band gap is called UV visible spectroscopy. And in UV visible spectroscopy, I have a chamber like this, and as shown in the figure, and I pass, I keep my sample on one side of the chamber, and then I pass a sample, I pass a beam onto the measurement sample, which could be in ultraviolet range, or it could be a visible range beam. Okay, and it's a monochromatic light. And the light which gets reflected off my sample is collected with the help of a detector, and I subtract the unwanted common signals with the help of a reference material and a reference beam. And the result is I get a reflectance spectra as shown here. And from this reflectance spectra, after performing certain post-processing calculations, post-processing steps, I get the band gap of my material. There is another characterization technique which is also fundamentally very important characterization, and which also utilizes the quantum effect for performing the operation, which is nothing but the photoelectric effect, and the characterization name is X-ray photoemission spectroscopy. So Einstein discovered the photoelectric effect in 1905, where he found that if a metal is bombarded with a light or photons, it gives out electrons, which means the photon knocks out electron from the metal, and the electron comes out of the metal with an energy which is equal to, which reflects its binding energy minus the work function of the metal, and that particular energy is detected with the help of setup like this, in which there is a hemispherical analyzer and slits, aperture, and there are the corresponding electronic setup to capture the right energy and the right energy window of those electrons. And now the speciality of this particular characterization is that if the energy belongs to a particular binding energy, we can immediately understand that this is a characteristic of a particular element. Suppose the electron has an energy equivalent to 532 um, electron volt, and that is a characteristic of oxygen. And we understand that my system has oxygen. And now why it is important, because we already started with a particular element in the PLD system, and we got the thin film of that element. And now why I need to check again whether that element is present? It is because suppose during the course of our synthesis, there could be an addition of defects within the system, which can influence the quality of the material, and thereby the qubit which we make out of it, which can actually influence the spin of the qubit, if it's a magnetic impurity or magnetic defect, or if it is some kind of other kind of electrical defect, then it can influence the electrical property. It can send electric fields and thereby change the state of our qubit. So in order to avoid all that, we need to know whether my system is pure. It has only a particular element or particular elements which we desire, and also they are in the correct state, because there are certain situations where we have different chemical states of the same element. So to avoid all that, we need to perform all these characterizations of the quantum material. And finally, there is something called electrical characterization, and this is very important to analyze not even the material, but even the qubit itself after it is being prepared. Here we use a very low temperature setups called as cryogenics or cryosystems, cryocoolers, and these can go up to very low temperatures, less than 4 Kelvin. And we perform, in the case of electrical characterization, measurements that can read out the way electrons are transferred from one point to another point. And these are important to understand, because if we are to control the spin of a single electron and maintain that spin in that particular site for a long time, so that we can perform the next gate operation, then we need to understand about how what is the mobility of that spin, or what is the rate at which the spin hops from one side to another side, and things like that. So to analyze and characterize such electrical transport properties, we need to perform characterization. In addition to the previous ones, we need to perform an electrical characterization also. It could be resistance versus temperature, simply a resistance measurement, or it could be a magnetoresistance measurement, where we also pass magnetic field along with measuring the resistance. It could be also something like a differential conductance measurement, in which we are measuring a di by dv, which is the current differential by current and voltage, current differential by voltage differential, versus the voltage measurement. So it could be anything like that, which gives us a window to look inside our devices, qubit systems, and understand what's happening there. In addition, there's something else in addition to these slides, that is called the lithography technique. And it's a very important step in order to fabricate qubit systems. So in the lithography techniques, lithography technology, we use photoresists and UV light to imprint layers on our chip, and a most important layer, which I will be discussing today within a few minutes, is a gate layer, and that's a metal, and before I deposit, or before I lay down a gate layer, I also lay down a dielectric layer, which acts as an insulation between my sample and the gate. And it's normally an insulator. And the gate is a metal. So there is no way of shorting between the gate and my sample. And this is done with the help of a lithography fabrication procedure. And why it's important? Because now I can influence the carrier density within my sample by changing the polarity of my gate. So I apply a voltage on top of my gate, and that can influence the electrical transport properties within my thin film, which is underneath the gate dielectric layers. Now, there are very challenges to create qubit systems which are really good. And what are those challenges? And this has been plaguing the people in this field for a very long time, and still even now, and various research are being conducted to reduce these challenges, to find a way around these challenges, so that they can make a robust qubit system with the desired properties. And the first and foremost is the decoherence effect and the quantum errors, which is what I already told you, that the qubit, if it interacts with the environment, that's a very bad thing to happen, and that it results in a measurement of the qubit's state, and it will destroy the superposition, and the qubit will collapse into one of the states, and that's called decoherence, and that is not at all desired. And there are other things like quantum errors. It could also be something like a T1 relaxation and T2 relaxation, in which the qubit can, without any external influence itself, it can simply get diminished. It can lose its state by own. And then there are something called the intercoupling of between two different qubits, and that also results in the decoherence and dephasing. And in fact, we want the qubits to talk with each other in a coordinated way, so that whenever we want to perform a two qubit operation, it does not cause a trouble. It shouldn't be that our qubit, a single qubit, is completely isolated from the rest, and it cannot be communicated. It cannot communicate with the neighboring qubits, or maybe any other second qubit. That shouldn't be there, and also it shouldn't be that it keeps interfering with other qubit and changes the properties of the other qubit, and we lose the state altogether. So these are challenges, and various methods like quantum error correction are being implemented to address these challenges, but that cause additional challenges, such as the overhead issues and additional lines and additional complexities of the architecture. And one of the crucial challenge is the scalability, because as we have discussed various algorithms in the last session, to perform while we were drawing the circuits of the algorithm, let's say Deutsch algorithm. I also had drawn a set of auxiliary qubits, ket y, at the bottom, right? And these are not involved directly in the calculation, but rather their existence is important for the circuit. And without these qubits, we cannot perform the quantum computation. And these are called ancillary qubits, and they are implemented by physical qubits in a real hardware system. Maybe or definitely they are not logical qubits, which are directly involved in the computation. So when I increase the scale, so when I go to a higher number of bits, higher number of inputs and higher number of bits, at that time these ancillary bits also increases along with it, and that results in a humongous chip and architecture hardware, and it will be a problem in such a case. And issues like control and calibration that deals directly with the type of platform which we are using. We use microwaves, waveguides to control the qubits, and also to read out the qubits. And certain qubits, they lose their state and we need to recalibrate them. So there are so many challenges such as that. And also in the case of flying qubits, flying qubits is a term used for qubits that are employed for communication, where it doesn't just stay at one place and store information like in the case of a memory, but it can perform the job of connecting a set of arrays of quantum qubits with another set of qubit arrays. Or it could be a free space flying qubit, which is nothing but a photon, which is also a qubit, and it can take information from a location to another, which also are used in cases like the quantum teleportation, where which we discussed in the class previous to yesterday, in which the two parties were sharing the same entangled pair, right? And that can be achieved by using a photon. So all such things, if they are connected together, such as in the case of an enemy center qubit platform, there is an interconnection between photon and the qubit, and that causes more overheads and challenges unique to those cases. And of course, there is manufacturing maintenance costs and reducing of measurement errors. So in summary, there are two main things that are the focus of the research community today as challenge, and they are the scaling, that is the number of qubits, which are really important to perform complex calculations, because if we don't have the infrastructure or we don't have the number of qubits, how do we perform the calculation? So we need the number of qubits, and these had an exponential increase in the early days, such as the transistor miniaturization followed the Moore's law. We had an exponential dependence of increase in number of qubits in the early days, but now the focus has been shifted to some other things like the fault tolerance or the error mitigation and correction, and hence the number of qubits have become saturated, and there is less attention, and that exponential growth has plateaued. And the second thing is a coherence time, which is directly related to the dephasing and decoherence caused by the environment on the qubit. So these are the points which we need to bear in mind while understanding different qubit implementation platforms. Now we have I give you an example now, and that's related to a system called silicon germide, or SiGe, which is grown on the substrate silicon Si. And this material is grown by a method called CVD, or chemical vapor deposition, and that's a very efficient method that results in very least defect and least disorder. And you can see in the picture here, which is taken from a characterization process which called as HRTEM, and which is short for high resolution transmission electron microscopy. TEM stands for transmission electron microscopy. And it will efficiently captures the image of the interface between the two materials. And we can see the silicon is in the bottom, is shown in dark, and silicon germide, which has a higher atomic number than silicon, is brighter, and it is on the bottom. And there's a clear demarcation between the two, and it's a very sharp interface, reflecting the quality of the film. And the TEM functioning itself is a quantum, if a quantum inspired, quantum induced functioning, just as in the case of XPS, which is photoelectric effect. TEM is also works on the principle of electron diffraction, or ED. And in this, the wave nature of the electron is utilized to generate useful information from the system. So in the 1923, de Broglie, scientist, had discovered that the matter has a dual nature, that it is not just a particle, it can also have a wave nature, and the wavelength of the wave associated with the matter is given by h by mv, where m is the mass and v is the velocity of of the object. And now here in this case, the electron is the matter, which is accelerated onto your sample, which is silicon germide silicon, and with some velocity. And higher the velocity is, the lower the wavelength, and the lower the velocity, higher the wavelength. So the wavelength is adjustable by the velocity of this electron. And if the wavelength, as we discussed in the case of an XRD, if it has 1.5 angstrom, which is matchable with the lattice parameter. In the same way, if the wavelength of the electron matches with the lattice spacing of, or rather the atomic spacing, because all these things are different atoms within this material, then we will be able to clearly distinguish one atom from another with a very high spatial resolution. And we obtain an image such as this. So this is something we used a quantum effect to get something useful. So here we are trying to make a qubit out of this system, SIGE, SI. And the first step to that is to understand that this interface of both the system is well known for something called an emergence of a 2DEG channel, or two-dimensional electron gas channel, where the electrons can accumulate in a thin two-dimensional layer near the interface. And this is possible when we grow a gate here. A gate, we lithographically fabricate a gate and apply some voltage, gate voltage. Okay, I'll share. Just a moment. Okay, so as I was saying, under the application of the gate voltage, the electrons are pulled from the bulk, or I think from the SIGE, from the bulk, it is being pulled to this particular interface near to the particular layer near the interface, and that is the 2DEG layer. And and as a result, the system, which was insulating in nature, it starts becoming conducting, because now I have the electrons in this layer, and under the application of an electric field, or under the application of a voltage here along this direction, I'll be able to get a flow of current, and I can measure it, and I find that the system is conducting. Now, apart from this experiment that I performed, there is another study which is by measuring the resistance. That is, this resistance, applying this through these electrodes, applying voltage to these electrodes, and at different magnetic fields, I can measure the carrier density in this layer, and also the mobility of those carriers in this layer. And what is the advantage of measuring these two things? It will help us understand whether there is any disorder present in the system. And disorder can also be something like a vacancy. It could be some dislocation, or some kind of dislocation, or an amorphous phase, or a different crystallographic domain. So it could be many things. Disorder could be many things, and mobility is the transport behavior of the electron. And if it comes across a disorder such as this, it will not be able to move forward. It gets restricted there, and that is a signature that there is some kind of disorder in the system, and that means it is not a very good quality system, and we will be it will be an obstacle. Maybe we can create a qubit system out of it, but if we are looking to scale up, then it would be an obstacle, because the such kinds of defects will multiply, and it would hamper the process of a multi-qubit system, creation of a multi-qubit system. So with that, we can start. We can start learning about the different qubit platforms which are well known in the literature, and also favorable candidates of research studies all over the world. And before that, there are certain criteria which was laid out by Division. So in the year 2000 or near to that, and he said that for the creation, or for the creation of a quantum computer, there are certain criteria to be met. And the first one is a scalable, well-characterized qubits are required. And it should be, the 2 points are it should be scalable and it should be well characterized. So they are directly equivalent to saying that we should have a very high number of qubits, a large quantum chip, and we also should have a well characterized, or we should also have a fault tolerant qubit where the errors are very least. And secondly, these qubits must have very long coherent time, such as they should have a low values of T1, or high values of T1 and T2. These are the relaxation times and the decoherence times. And these qubits must be initialized, must be capable of getting initialized, and with high fidelity. Normally, they are initialized to a get zero state. And they can be operated upon by universal set of gates. A universal set of gates are normally all the single qubit gates which we discussed, along with the C0, which is a 2 qubit quantum gate. And finally, the final state can be measured and or read out. And another two criteria were also put forth to explain the quantum communication, which is not really quantum computation, but very related to quantum computation. And the first is that a stationary qubit can be converted to a flying qubit. So I already discussed about flying qubit. It could be a photon, or it could be another qubit, like an electron spin. And this interconvertibility should be there between the two kinds of qubits. And secondly, this flying qubit can be faithfully transmitted via repeaters. Repeaters can be thought of as intermediate amplifying stations where or nodes where these flying qubits or they come and get entangled with another set of flying qubit, and they will be transmitted with more robustness and with better um, coherence. Okay. So there are various qubit platforms or hardware platforms that are being proposed and that are also being implemented by various research labs and companies all around the world. And one of the one of the most promising qubit system is a semiconducting qubit. And why it is so is because we already have a large, a mammoth industry called the semiconductor industry that has been developed for many decades, which had uh, um, expertise in growing semiconductors under various challenging situations, and technologies for fabricating and characterizing the semiconductor structures. And to leverage, and by leveraging these facilities and techniques, we can prepare qubits in the form of electron spin in a semiconductor, and that has got a very long coherence time. And now how it is being done? So I already discussed about the gate fabrication and the metal gate fabrication on top of the semiconducting or metallic sample you have, and that results in an emergence of 2D electron gas at the interface. Right. A similar thing was also being carried out in the first quantum revolution here, where we had a transistor, and in the transistor, specifically if you look at the MOSFET or the field effect transistors, we have a gate. This is a gate, and we have a source and a drain. So we apply a gate voltage here, and we also apply at a transverse voltage along this direction also. And the gap you see here is because of the insulating dielectric present here, so that there is no shorting of gate with the sample. And as a result, the gate influences the current through this transistor, and it acts as a switch for in the electronic circuits. And this is the fundamental unit inside the IC chips which we are using in our day-to-day electronic gadgets. And the tuning of the electronic property or the transport property of this sample is with the voltage at the gate. So by changing the voltage, we will be able to tune the properties of the sample. Now imagine, instead of this sample here, we have a qubit. We have not yet a qubit, a potential qubit. And what I can do is, this is the This is the gate. This is a two-gate system. So I have a VG1 and a VG2, and I tuned the values of the VG1 and VG2 in such a way that I pull in electrons. I also push out electrons. If VG can pull electrons, it can also push the electron by turning its polarity in the opposite direction. And I created a situation where only once a single electron is under my gate. So is it possible? Yes, it's very much possible. And that has been experimentally shown. So suppose I don't consider this area, so I just increase the voltage here, and so that electrons are pulled to this area, and then I decrease this voltage, I go to the negative side, that will push out the electron. So something like that, in such a way that only one single electron lies underneath my gate. Okay. And such a system is called as a quantum dot system, and it has many other properties apart from qubit. So what exactly is the reason of the genesis of its formation is that a competition between something called a charging energy and a thermal energy results in the formation of this quantum dot. Now, what is a charging energy? It's a capacitance energy, in fact, and this capacitance is coming from the gate dielectric structure, where you have two conducting layers. One is the 2DG, and another one is your gate, and between them is your dielectric constant. And now if I apply a electric field here in the gate side, it results in a kind of a capacitance C between these two sides, and we model them as a disk, and the capacitance for a disk is 8 epsilon 0 epsilon r. R is the radius of the disk, and for so these are like the gate I grow on top of the sample will have a radius of r, capital R, and it ensures that a single electron spin is underneath it. And how do I ensure there's only one single electron? So I calculate this charging energy. For a single electron, the charging energy is E squared by C. And to ensure that this energy, there's only a single electron, I have to consider the thermal energy also that will be acting, because the electrons, they agitate and they move here and there due to the thermal energy. So if I make my charging energy sufficiently high, then an addition of a second electron to this space will be prohibited because of the huge charging energy compared to the thermal energy. So I check for different values. Let's say R equal to 10 nanometers. So I calculate the C. I have the values of epsilon 0 and epsilon R, and I calculate C. And then I find that this E squared by C is around 30 MeV. And for R equal to 100 nanometers, EC is 3 MeV. Now, I measure the thermal energies. And thermal energy is measured by using this formula, Kb into T, where Kb is the Boltzmann constant and T is the temperature. At 300 Kelvin, this is 26 MeV. So we see that it is less than 30 MeV, but it is close to 30 MeV. So 300 Kelvin is a good temperature where we can we can create such single electron spin under a gate, but it is not quite so because it is not very less. It's just 4 MeV less. That's it. But if I go, but if I have 100 nanometers, then it is definitely not a good choice for 100 nanometers, because the EC is 3 MeV, which is much less, and we will not be able to recreate a single spin here. Now, if I go to T equal to 4 Kelvin, and then the energy is much less, 0.35 MeV. Yeah, then it's a good, this is good. T is equal to 4 Kelvin is a good temperature where I can perform, I can have a quantum dot. Yeah, so from T equal to 4 Kelvin and T equal to 30 millikelvin is also good. So these are the temperature range where um, I can fabricate a quantum dot or a semiconducting qubit. And note that these are very low temperatures, and we need infrastructures of cryogenic coolers to achieve such temperatures and to maintain the qubits there, right? And now let's focus on to the physics of a little bit. So I have a situation like this where I apply a voltage at the gate, and these lines are the chemical potential uh, of the 2D EG. And these are the source and drain chemical potentials, or the source contact chemical potential work function and drain contact work function. And now I see that my electron is here it's present here, and it's at a higher energy compared to the work functions of the two contacts. So the source is called source because it acts as a reservoir from where the electrons move to the um, 2DG. So I have my let's say this is the source contact where I apply the transverse electric field, right? And here I have the sink for that, which is called as drain. And here I have the dielectric layer, and here I have the gate. So electrons start from here, and it moves here, and then it comes here, and then it goes out of here, and it goes to the sink. Now, when I have a quantum or qubit here with a spin, I want to preserve it there. I don't want it to move away from here. Neither I don't want another qubit to come here and disturb the state. So the chemical potential of this spin has to be a higher level, has to be very high, such that an electron from here, it cannot jump to this level. It doesn't have that energy to jump from this level to this level. Neither this electron which is present here, it cannot jump from here to here because this energy level is too low. It cannot do that. But I changed the voltage gate in such a way here, careful attention, that this is how I manipulate the qubit in the semiconducting qubit case. So if I change my VG, then I can bring down this nu n to this level here. Now you can see these two are in the vicinity. Now an electron can come from here to here, and an electron can go from here to here quite easily. And due to the exclusion principles, only one electron can be here, right? Two electrons cannot remain in a particular state. So by manipulating the voltage, the gate voltage, I can decide the occupation of my qubit. Okay. Yeah, so a few other points related to the semiconducting qubit. This is just a very crude prelude to semiconducting qubits or quantum dots. Quantum dots can also be used as very sensitive electrometers. Why? Because I have two quantum dots neighboring the neighboring sites, and suppose this was not there before. This was only introduced later. Then my gate voltage had some specific values upon which this qubit will have different chemical potential energy levels, right? Or a specific chemical potential energy level. Now, when I bring an additional quantum dot near to it, it causes a shift in the energy levels of this qubit. And thus it can be picked up by the changes in the VG, and hence it acts as an electrometer, a very sensitive electrometer. And normally the qubit control is achieved with the help of alternating magnetic fields, and it's a field in itself, and there are ways by which we can perform various quantum gate operations like the 2-qubit C dot operation or the phase gate operations, and etc. Now the main caveat of the semiconducting qubits is that we need to have a very clean space to fabricate this, such as clean rooms, which are of not of the standards of the university labs, but of the standards of the industries. It has to be that clean so that we can reproduce the qubit operations multiple times. And the other challenges of quantum dots are that the scaling of connectors is a big challenge, because as we increase the quantum dots, the interconnects between them and the flying qubit interconnects, and so there are so many other connectors, and these become so bulky when you scale up, and it will be difficult, it will be hard. And secondly, the environment of the qubit can also affect it in the form of nuclear spins, because if you consider materials like germanium arsenide, which is a common platform used in this particular case, it can it can result in nuclear spins. It has a non-zero nuclear spin, and that can affect the qubit. And the workaround to this is to use silicon host material with an isotopic purified silicon of silicon-29, because it has non-zero nuclear spin. And as I told, the requirement of low temperature infrastructure. The second method is NV-centered qubit. Here we use NV centers in diamond. So diamond is a arrangement of carbon atoms, such as shown here in the tetrahedral fashion. And in some locations, the carbons can go away from that location, creating a deficiency, and which is getting occupied by a nitrogen, and where it is accompanied by another vacant site, and thus we get an NV combination, which is a nitrogen and vacancy combination. And these kinds of locations in the diamond crystal structure are called NV centers. So what happens is, in the V, which is a vacancy, sometimes electrons with a particular spin can get trapped, and these can be used as qubit. Apart from the electron being used as a qubit, we can also use the carbon-13 nuclei, which have a non-zero spin, also as accompanying qubits, which is an added advantage for NV-centered qubits. And normally these are the memory qubits or the data qubits, and the electron acts as a kind of an interconnecting qubit, okay, or as a bus. And the advantage of these kinds of qubit implementation is that it can be operated in even the room temperature also, and it also has a very large coherence time, and it can couple with photons, and that opens a host of wide applications such as scalable computation and quantum internet. It can result in something called the quantum network. We can think of implementing such a quantum network where small scale QPUs, which are short for quantum processor units, can be interconnected, and using the photons and the NV centers present in the QPU can couple with these photons, and thus we can have a coordinated processes and achieve a very high computation using such as interconnected network. So this is a very hybrid qubit, as I already mentioned, due to its coupling possibilities of coupling with the photons, and also the presence of both nuclear and electron spin within the NV centers of the diamond. And they can be controlled by using electric field lines and also microwave lines, both having different purposes. Electric field lines are used to control the color of emission, so they have to emit the light in the form of photon for interconnection. And they also need to control the spin state, and that is achieved by the microwave lines, which are probably like I'm not sure, but it could be fabricated lithographically on top of on near the NV center of the diamond, and it will feed microwaves through these lines. And there are various tricks performed to extract maximum light out of it using solid immersion lens sculpted out of the system itself. So there are various challenges, such as the nearest neighbor coupling of NV centers is a dipolar interaction, which is a short range interaction and can not achieve a long range interaction. So we can only make short arrays, and with the help of photons, we can have a larger one and in the form of quantum networks. However, there are overheads associated with that. Defects can get incorporated while performing the ion implementation and nanofabrication methods. The room temperature operation is possible, but the fidelity is trade-off. It's a trade-off, and fidelity is the measure of the coherence, basically. So if your system decoheres at room temperature, then it has got a low fidelity there at that temperature. And the photon mediated entanglement is possible, but it's a slow process. And finally, the inefficient light emission. Another system is the neutral atoms. Here we use hundreds and thousands of atoms using optical tweezer arrays, which are multiple laser beams that intercross with each other and forming an array of intersections of laser beams, where you can trap the atoms in those crossing points, and excite these atoms. And excitation can actually lead to different gate operations, such as the two qubit gate operations and so on. Here the atoms are movable, and hence no geometric constraint. We can also have parallel execution, many gate operations called as global control. Okay, so these are this is a very new area, neutral atoms, and some of the challenges are these are very slow processes, like atomic movement and readout. So we need to have atom movement because these optical tweezers can be shifted slightly here and there. So it is possible to move the atoms, and quite conveniently, and it doesn't take. It's not a very difficult job, but it's a slow process. And also, these atoms can quickly forget the information, and thus a fresh loading of new atoms are required in a continuous way. And the next qubit platform is something which is being implemented intensively in the present day by various companies, including IBM, Google, etc. Intel also. And this is called superconducting qubits, which has got a lot of promise, but not without challenges and caveats. And there are various superconducting qubits, such as fluxonium, flux qubit, charge qubit, phase qubit. And transmon is a special kind of charge qubit. And basic unit here is a junction formed by two superconducting islands, and this junction is called as Josephson junction. And this Josephson junction has a property of having both an inductive coupling as well as a capacitive coupling. While the inductive coupling allows the qubit to have a kind of in fact, it allows for the charge to move from the charge carriers. In fact, these are Cooper pairs. Cooper pairs are the charge carriers in superconductors. They can move from one side to another, aided by this inductive coupling. And sometimes they prefer to stay here without moving, and that is aided by the capacitive coupling. So they have an opposite a coordinated kind of functions, and these are two functions or two natures of this Josephson junction. Okay, and now how is it different? It's a very new kind of a platform which we have not discussed yet. We have been discussing about the semiconducting qubits where electron spin was used as a qubit, and the NV centers where also the electron spin was used as a qubit along with the nuclear spin also. And then the neutral atoms where yeah, so in the neutral atoms we used not the electron spin but the atomic levels within the neutral atom. They are, so the individual atoms are used as qubits. Okay, not the spin energy levels. But in the case of Josephson junction superconducting qubit, we are using something else to be the qubit. Okay, it could be different, but here we are using a transmon as a qubit. That is the name of the qubit, transmon qubit. And what exactly is a transmon qubit? It's an artificial atom. This is not something which is presented by the nature. Earlier we saw electron spin and nuclei spin, they are all being presented by the nature. It's already there in the nature and we are just using it, picking up and using it, fabricating a nice environment for it. But here we ourselves are fabricating the artificial atom through the means of thin film and lithography technology. We are creating the superconducting islands, and we are adjusting the inductance and capacitive coupling. So hence it's an artificially created qubit system. And apart from the earlier electron spin and nuclei and atomic levels spin qubits, we have a multiple qubit system. In the electron spin, we have clearly two distinct energy levels. In the case of atomic level spacing, so yeah, so this is basically atomic spacing, atomic, and so there are like multiple levels, but the energy spacing of the higher energy levels are very small. Hence, they will not, and they are very far away. They are very far away, so hence they are not. They are kind of considered as continuum, and they are not very. They are not important. They are not considered in the qubit implementation. So this is the main two levels that are being used for performing the qubit operations. That is the 0 and 1 levels of the qubit. But in the case of superconducting qubit, in the case of transmon, or rather, it's not the case of transmon. In systems like transmon, systems like Josephson junction, are systems where both inductive and capacitive coupling are present. We get such a multi-level qubit system. And now you may wonder how this can be utilized, because now I have multiple levels, which should be the 0, which should be the 1. That is a confusion, right? So we'll just dive a little bit into that. And so this can be visualized in this form, where I have two superconducting islands and they are being connected by a capacitor and an inductance L. And if we are just focusing on L as a normal inductor, then we will find that the Hamiltonian of this system or rather the energy of the system, can be expressed as this form: q squared by 2c plus phi squared by 12, where q is the charge and the on this islands, and phi is the flux, um, right, the flux along the inductor, because we know that inductor has a flux associated with it, magnetic flux, and this is the standard equation for the LC circuit, right? So here you have an LC circuit, and using this equation we find that the resonance frequency for the LC circuit is omega equal to 1 by root LC. How we get that? It is equivalent to another system such as a mass spring system, where you have the position of this mass encoded in the x variable, and the momentum of the mass is encoded in the p variable, and the energy can be written as x squared by or rather half k x squared, which can be written as x squared by 2 into 1 by k plus v squared by 2m. Now see the equivalence between these two equations. So we from the analysis and the standard physics textbooks, we know that this is a simple harmonic oscillator which have energy spacing such as this: h bar omega. H bar omega is the energy spacing between the adjacent two energy levels. So the LC oscillator also will have a similar equidistant energy spacing. However, this is too bad for implementing a qubit, because we don't want equidistant energy spacing, because then the qubit will get confused like us, that which should be my 0 and which should be my 1. It might choose a 2 and 3 as 0 and 1 in one instant, and it might choose 1 and 2 as 0 and 1 in another instance, and it will completely mess up the qubit space. Or it might invite another qubit, and it will also stay in some other energy state, which will destroy the qubit space. So the how we implement this is by using a different kind of L, and that's where the Josephson junction comes into picture. We do not we do not have the Josephson junction is not a normal inductor, or it doesn't act as a normal inductor. It's a different inductor. It's called as Josephson junction inductance, and it has a relation with the current in the form of a sine wave, sine of 2 pi phi by phi 0, and the result of that, it's a slightly involved calculation. What we get is we get a broader energy levels that has different energy spacing. So this spacing here, it is around 300 megahertz less than this spacing here, and that is sufficient. That is sufficient for our qubit to not get confused and choose this level as get 0 and this level as get 1. It will not go to this level here, because it is too far away for the electron occupying this qubit, or rather not electron, the qubit, the superconducting qubit occupying this level. Okay, so that's how we design a Josephson junction based superconducting qubit, or a transmon. And to how do we operate these qubits is using a transmission light resonator, which are these long pads seen here. They are coplanar waveguide resonators, which are imprinted on the chip along with the qubit, which is represented as the Q1. And these are used to control the state of the qubit. That is whether it is in the 0, 1, like whether you need to change the state or the sign. And to read out the kind of what state the Q1 is in, we use another resonator in this form. And in some cases, like Google has created two inductors, which are parallel to each other, and the reason for that is that they can apply a magnetic field in here, which is generated with the help of some flux bias lines, and that will be also connected to this qubit flux bias lines, and that will change the inductance at will. So they can control the inductance value, and by controlling the inductance value, they will be able to change the omega, right? Omega is 1 by root LC. So they can change the qubit frequency, and by changing the qubit frequency, they will be able to play around with the operations that can be performed, single qubit operations as well as multi-qubit operations, etc. Now, various challenges are there. Although this is the most promising platform, it is not rid of any issues or caveats. The first primary issue is that it has got a low fidelity, and it is also affected with control line interference. That is, these lines, they can not only change the values of qubit, or it not only it can control the qubit frequencies, but it can also affect, suppose let's say this readout line frequencies and modes, and it can induce new transmission electric field modes, TE modes, and all those things. So such control line interference are possible. And normally, I think I haven't said this. So this is a microwave waveguide. Why microwave? Because its frequencies are in gigahertz, and that matches with the qubit frequency. So it can resonate with it. And then another challenge is the low temperature challenge. And then another one is the qubit variations. So I said in the beginning that this is an artificial atom. It's not something which is presented by nature. So we are manufacturing it. And the problem with the human manufacturing is that every time we manufacture it, it will have different parameters. It will not exactly have the same parameter. So when there are different parameters for different qubits, when we scale up, it will become a huge issue, because there will be mismatches and in the frequencies and so on. So there are issues with that. And obviously, the scaling of interconnects is a problem in superconducting qubits also. And there can be situations where the qubit can get excited to higher energy states, although the energy differences have been adjusted with the help of Josephson junction inductance. And another popular and very promising qubit platform is the ion trap qubit. Here we use ions, individual ions that are trapped using stable lasers, and the qubits are encoded in these individual ions or atoms. So we can perform functions like we can prepare the state, we can read out those ions, in the qubits encoded in the ions, and we can perform single qubit gate operations as well. And these are carried out by using microwave or laser fields. And we can perform 2-qubit manipulation also, like the C0 gate, through interconnections between two traps, two ion traps, with the help making use of the normal mode vibrations of their interconnection. And it can be performed within tens of microseconds. And these kinds of ion traps have got high fidelity because they are highly isolated in one particular trap. So they do not have much connection, and thus they have a very high fidelity. However, when you scaling of such ion trap qubit platforms are a challenge, because when you scale, you need to have a lot of interconnects, and you need to apply a lot of complex operations to shuttle the ions from one spot to another spot, because they are quite comfortable in one site. And companies like IonQ, Honeywell, they have implemented this promising platform for quantum computer. Another new quantum qubit implementation field, uh, which is a very promising one, and which is a very recent implementation by Microsoft. It's a topological qubit where they use something called the Majorana fermion states, and these are existing in the system as zero bias modes, and we can perform the gate operations using braiding operations. And these are having error correction implicit in their hardware level itself due to their very nature, due to their very physics, which is called the topological protection. And I will be discussing more about this in tomorrow's class, which is about the applications of quantum computing, and in the context of Microsoft's new qubit implementation, Majorana 1. And it's named after a famous physicist from Italy, Ettore Majorana, who did a lot of study in this field. And this can also be, there are many materials which are famous for, which are potential for exhibiting Majorana states. One such system is shown here, where you have a superconducting electron-topped BABIO3 and the whole topped BABIO3, which is a superconductor. This is a superconductor, and this is a phase called a topological insulator, which has exotic surface states with spin momentum locking, electron transport, while the bulk is an insulator. And this interface of these two systems is a promising platform for observation of Majorana fermions. And that can act as a topological qubit with extra protection given by the topology of the system, and thus it can encode qubit without fear of environmental interference into it. Another application of the quantum computing, it's not in directly as a quantum computer, but in the form of quantum internet. And this can be thought of in two ways here. One is a quantum random number generator, QRNG, in which case we send a photon to a beam splitter, and a photon is a qubit, right? It is a qubit, and qubit information can be encoded in the polarization of the photon. And now if it falls on the beam splitter, it can actually create a superposition of photons. So you get two clicks on two detectors which are kept at 0 and 1, which means there is a superposition. And by this, this is a very crude way of introducing this concept. However, we can use this in a very practical day-to-day life kind of a scenario, which is your camera in the mobile phone. That can use this QRNG technology, and I don't know much about it, but I just know it's a advancing field, and you can actually do a lot of things with this QRNG in the camera, mobile phone. Another interesting field is the quantum key distribution, or QKD, where you can distribute the entanglement created, and can enable it to transmit to very long distances, around more than 100 kilometers, around 300 kilometers or so. The photonic transmission photons can be used as a flying qubit, and you can achieve transmissions up to 100 kilometers, but that's limited up to that. But if you use a distributed entanglement technology, and there are, I think, the technologies, so you can you can create different nodes, shared nodes, where the entanglement is strengthened or re-strengthened, and then it can be further transmitted, and hence it will let far distance quantum communication possible. Yeah, so with that, we'll come to the end of today's qubit implementation session. And tomorrow we'll be discussing about the applications that quantum computing has. And we also discuss about the Majorana fermion these are topological qubit implementations as well. So if you have any questions or comments, you can shoot it right now.
Okay, sir, if you don't have any questions to be addressed, we can wind up for the day. Thank you, sir. Thank you so much for your informative session. Like tomorrow, we off of Independence Day, we don't have a session. We are again meeting on Monday. So the fifth day of FTP session will be on Monday. So yeah, dear faculty members, tomorrow and day after, like Saturday and Sunday, which we don't have a sessions. So again, we are meeting on Monday. The 5th day will be on Monday. Okay. So I hope you all understood. For all the 3 days, is like Friday, Saturday, Sunday, we don't have any sessions. Okay, so related to attendance, okay, I'm requesting you all, please mark your attendance without any fail. As attendance is mandatory, you have to get the 60% of attendance, then only you will get the certificate. So make sure that you will be marking your attendance every day. So, which I have shared it already on the chat. I have shared it once again. Kindly mark your attendance. Okay, we will wind up for the day. We all meet by Monday. Thank you all. Thank you for joining. Have a great day.